Hello everyone, this is going to be another video about the wave equation. So in my last video we found the general solution of the undamped wave equation. This time we're going to solve it including the damping term, which is this gamma dy by dt term in the middle there. Now if you're interested in where this comes from, I derived this for the case of a string a couple of videos ago. For this video we're just going to take this equation as a given and think about how to solve it subject to certain initial conditions and boundary conditions. So our initial conditions are basically going to be that there is no wave initially. So mathematically, how can you write that down? Well, if there's no wave, that's like saying the displacement y evaluated at any position x, but at a time of 0, t equals 0, is just 0, right? But if there's no wave, that also implies that there is no motion initially. And so we can say the first time derivative, y dot, is also 0 at any position as long as t is 0, right? So we can say y dot of x and 0 is also 0. So both of those things are equal to 0, y and its first time derivative. Now to illustrate the boundary condition that we're going to apply, in addition to those two initial conditions, let me draw a little diagram. So this is going to be our string. Let's think of it as a wave on a string, although this could equally well apply to other types of waves. So your x-axis is running along the length of the string. It's not doing anything initially. We're going to say it's what I would call a semi-infinite string. So it starts at an x value of 0. So x equals 0 is over there. But x can get arbitrarily large, right? So it's the string has an infinite extent in one direction, but doesn't exist to the left of that point that I've just drawn there. So what we're going to do is take the end of the string at x equals 0, and basically just shake it up and down, and the time dependence of how we are shaking that string up and down is going to be specified by some function which we'll just call f, right? Now, mathematically we can write that down as saying, well, y, the displacement y, at an x value of 0 but any time t is equal to f of t. And I'll also just note down on the diagram that we're interested in solving the wave equation in the region where x is bigger than 0, because we already know what the displacement is when x is equal to 0, right? It's just f of t, and there is no string when x is less than 0. So we're specifically solving the wave equation where x is bigger than 0. So I'm going to use the same sort of method that I used to solve the undamped wave equation, which is take a Fourier transform in the time domain of the entire partial differential equation. So let me just put down the definition I use of Fourier transform. There you go. Y tilde of x and omega is the integral of y of x and t times e to the minus I omega t with respect to time, overall time values. And under this convention, the inverse Fourier transform looks like this, where you do y tilde times e to the positive I omega t and integrate overall values of omega, and then you have to divide by 2 pi as well. So we're going to be using both the Fourier transform and its inverse in our solution. So let's see what happens when we take the Fourier transform of our partial differential equation. Well, the first term is a second time derivative of y, and we know from the last couple of videos that differentiation in real space corresponds to multiplication by I omega in Fourier space. So the second time derivative brings down a factor of I omega squared, and then you've got your Fourier transform y tilde of x and omega. Now the middle term, this damping term, is just going to turn into plus I gamma omega. You pull down a factor of I gamma omega times, again, Fourier transform y tilde of x and omega. Now the third term, the minus c squared d2y by dx squared, you can't use that kind of trick because that's a spatial derivative, not a time derivative. So we're just going to have to leave that as minus c squared d2 by dx squared of y tilde, which is a function of x and omega. All of that is equal to 0, because when you Fourier transform 0, you still get 0. So let's just tidy that equation up a little bit and write it in a more concise form. What you'll end up with is y tilde. I'm going to omit the x and omega dependence, but we know that's a function of x and omega. I'm going to put double prime for the second spatial derivative, so that y tilde double primes come from the second spatial derivative in the previous line. If you collect the other terms together and divide everything by c squared, you get that second derivative plus omega squared minus I gamma omega over c squared times y tilde. That's all equal to 0. In doing so, we've used the fact that I squared is minus 1 from that first bracket there. Now this is basically the equation of simple harmonic motion. The only slightly strange thing about this is that what would usually be our angular frequency squared is really a complex number here, but we can still quote the general form of the solution to the SHM equation. So let me just write that down. I'm not going to derive it here, but the general form to that equation, the general form of the solution to that equation would be y tilde is some constant times e to the I qx. I'm going to define what q is in a moment, plus some other constant b times e to the minus I qx. Q is the square root of the coefficient of y tilde. So it's the square root of all of that stuff. So let's just write that out. Q is omega squared minus I gamma omega all over c squared. And let's do that as a power of a half. Okay, I'm just going to add some subscripts. Let's subscript the q with an omega to remind us that it's not a constant. It depends on omega. Let's put those subscripts in there. And also, because remember this double prime was a partial spatial derivative, our a and b are again not really constants, but they could depend on omega as well. So now we've solved for the Fourier transform of y. So all we have to do is inverse Fourier transform that solution that we've just got. So if I apply the inverse Fourier transform, we find that y of x and t is, well, it's an integral from minus infinity to infinity over all values of omega of a omega times e to the I. Now, from your inverse Fourier integral, right, this term over here, you get a positive omega t, and you're also going to have a plus qx in your complex exponentials exponent, right? So you can combine those exponentials together and get e to the I times omega t plus q subscript omega times x. Now, the b term is very similar, with one difference, right? So the I omega t part is still positive, so I can write it as I times omega t, but now the spatial part, the x part, has a minus sign, so minus q omega times x. That's all integrated with respect to omega and divided by 2 pi. Now at this point, we're going to use some physical reasoning as opposed to purely mathematical reasoning to eliminate one of those terms. And so let's just take a moment to think about the interpretation of the a omega terms and the b omega terms. Now, this first term, where you've got a plus sign in your complex exponent, physically represents some kind of waveform traveling to the left, while this second complex exponential with the minus sign between the t and x terms physically represents a waveform which is traveling to the right. That basically follows from the way that graph transformations work. If that's not obvious, then I recommend that you have a look at my previous video where we talked about the undamped wave equation, and I discussed that in a little bit more detail. But basically, the first term corresponds to a wave moving to the left, while the second term corresponds to a wave moving to the right. Now, if your semi-infinite string started with no wave on it, and you suddenly start shaking it up and down at x equals 0, the only way you could end up with a left traveling wave would be if it was reflected from somewhere, at some large positive value of x. However, it's an infinite string. It doesn't have any boundary for waves to reflect off. And so we can deduce that there can't be any a omega component, right? That would require some reflection, but there's nothing to reflect off on our string. So we can pretty much just eliminate that first term on physical grounds. And so that nicely simplifies to just an integral, again, over all values of omega of b omega times e to the I. I'm going to do one more thing at this stage to rewrite a complex exponential. I'm going to factor out this omega and do is I omega times t minus q subscript omega divided by omega times x d omega over 2 pi. The reason why I factored out that omega there is to make this look a little bit more like an inverse Fourier transform. Now we can find out something interesting about this b omega coefficient by applying our boundary condition. So let's do that. Our boundary condition said, remember, that y of 0 and t is equal to some specified function f of t. So if we plug in x equals 0 into that, solution that we've got there, we're going to find that the integral from minus infinity to infinity of b omega and then just e to the I omega t d omega over 2 pi is supposed to be equal to f of t, right? Because the x term just disappeared when we substituted in x equals 0. Now, you can probably spot by inspection that the integral there is just an inverse Fourier integral, right? And so by inspection, you can see that b omega has to be the Fourier transform of f. So we can conclude, let me just write down here, that b subscript omega is the Fourier transform of f. So I've just had to make a bit of space. I've got a summary here of where we are so far. Here is our current solution for y of x and t, where q omega is this parameter here. Now, in fact, without any further information, this is basically the solution, right? We're not always going to be able to write that integral in a nicer form. However, it turns out that in a certain limit, the limit of light damping, this simplifies to a very nice intuitive form. So let's think about how that works. Let's go back to our q omega expression and just rewrite that a little bit. I'm going to factor out a factor of omega over c. So if you've got your brackets which are square rooted, that leaves your first term as 1 and your second term as minus I gamma divided by omega. That's all to the power of a half. So we can do a binomial expansion on this, and under certain conditions, under light damping conditions, only a couple of those terms are going to be significantly large. So I'm going to write down here, just to be a bit more precise about under what conditions we can do this. I'm going to say if gamma is much less than omega. Now think carefully about this, because remember that omega is not actually a constant. It's something that we're integrating over. So technically I should say here, if gamma is much less than omega for all frequencies, whereby frequency I just mean omega, for all frequencies present in the Fourier transform of omega. By that, what I mean is, well, it'll depend on the function f of t, like how quickly you're shaking the rope up and down, basically, because not every function is going to have a very wide range of frequencies present in its Fourier transform. In order to do this binomial expansion, we basically just need gamma to be much less than all of the frequencies which contribute significantly to the Fourier transform. So under those conditions, q subscript omega becomes approximately equal to, well, you still got your prefactor, omega over c. If we just take the, well, first order approximation, so 1 minus I gamma over 2 omega, right, ignoring the higher order terms, which is, well, it's omega over c minus I gamma over 2c. So if we substitute that approximate q omega back into our integral, right, into that complex exponent, then we're going to arrive at the approximation that y is roughly equal to, so again, integral over all values of f tilde of omega, e to the I omega, so t stays as it is. Your omega over c here is going to contribute a minus x over c term when we sub that into there, right, because the omega on the denominator there cancels with the omega on the numerator there. Then you're going to get an additional plus I gamma over 2 omega c, again multiplied by x, right? And then that's it, because we've ignored the higher order terms. That is an integral d omega, and then divided by 2 pi. Now if you pay special attention to this final term here, the I gamma over 2 omega c times x, notice that when we expand the brackets out in the exponent, the i's are going to combine to give you a minus 1. And the omegas are going to cancel out, and that's going to leave you with a term which is completely independent of omega, right? So that final term we can actually take out of the integral because it's independent of omega. Now if we do that, something quite nice happens. You get e to the minus, well, it's going to be gamma x divided by 2c, because those omegas cancelled, right? So we've taken that out of the integral. The integral itself is now overall values of f tilde of omega times e to the I omega. The only terms remaining in your complex exponential are t minus x over c. We integrate d omega over 2 pi. Now this integral here is just an inverse Fourier integral, right? Except instead of the t in our general definition up there, we've got t minus x over c in its place. And so this actually simplifies to e to the minus gamma x over 2c times f evaluated at a time of t minus x over c. Now how do we interpret this? Well, firstly, just focus on the f of t minus x over c part. What that's saying is that at some particular value of x, to find out what the displacement there is, you take your function f and evaluate it a time of x over c into the past, right? Because you take the current time t, you subtract off x over c. So that means that the displacement at some value of x is the same as the displacement at the origin, x equals 0, a time x over c ago. Now, if you think about the fact that speed equals distance over time, or time equals distance over speed, you should be able to convince yourself that that is all consistent with the idea that c is the speed of the wave. Now, this term in the front, e to the minus gamma x over 2c, is just a decaying exponential, a spatially decaying exponential, and the characteristic scale of that exponential decay is set by gamma. So remember, gamma is related to the damping coefficient. So if gamma is very large, then the exponential decays very quickly, and so the information that you're providing to the string by shaking it up and down according to the function f of t is propagating along the string, but also the signal is sort of decaying spatially as it propagates in. If the damping is heavier, then the signal will decay more quickly, which is, of course, all consistent with what we'd intuitively expect. Anyway, if you've made it this far, thank you for watching. I hope you've enjoyed, and I'll see you again soon.